In our previous videos, we've looked at what statistical tests to use if you are comparing your variable to a value, whether it was nominal, so categories, ordinal, or it was a count or measurement, so ratio or interval. We've looked at what if you have two groups and you're comparing the two groups to each other, different tests depending on whether or not you have different people in the groups or the same people. If you have different people in the groups, then we use Fisher's test if it's categories that we're comparing. If it is rankings, we use Mann-Whitney. And if we have measurements or counts, we're using our two-sample t-test. If we have two groups and it's the same people in the two groups, so we're comparing before and after, often we're looking at measurements over time. Then if it is categorical information, nominal data, we use the McNamara. If it is rankings, ordinal, Likert scale, we can use the Wilcoxon rank sum test. If it's ratio or interval, where measurements or counts, we use the paired t-test. We can also compare three or more groups, and we look at, are there different people in the three groups, or more than three, or is it the same people in all the groups? And so repeated measures over time. If it's different people in each group, then if it is categorical data, we use the chi-squared test of independence. If it is ordinal, ranking, Likert scale type, we use Kruskal-Wallis. And if it is ratio or interval, so we have measurements or counts, then we're looking at the one-way ANOVA. In this video, we're going to focus on what if we have three or more groups. We have the same people in all the groups. So just like those paired tests before, but now we have not just before and after, but maybe we have before, after, and then after something else. So maybe we have 3 periods of time where we have the same questions asked 3 times, and we're seeing if it is different. So we have the same people in all 3 groups or more than 3 groups. If it is categorical data that we're comparing, then we use what's called Cochrane's Q. If it is ordinal data, we use the Friedman's test. And if it is ratio or interval data, and we can assume a normal distribution, we use what is called the Repeated Measures ANOVA. If we don't know that it's normally distributed, or we know it's not a normal distribution and has another type of distribution, maybe it's skewed, maybe it's uniform, then we go with the Friedman's test. So let's take a look at how to do these in Python. So just a reminder, if you're working along with us, I'm just going to figure out where I put it. We have our workbook in drstephpowers.github.io/BIA. We're doing the inferential statistics. Click here and get the workbook to load into Google. And then you'll also need the files, Excel files that we're loading. And so you'll find those files here. We've been using Bargain Numeric. It's the coded version of our collective bargaining survey. And we've been looking at, where's my CRM clean, to look at what if we have a customer relationship management database. And so you'll need those two. And then, of course, if you're going to pull them from your own Google Drive, mount the drive and import them in. All right, let's continue on. So we're most of the way down this worksheet. We're looking at a difference between 3 or more groups with the same people in each group. So let's look at how a Cochrane's Q works. To do the Cochrane's Q, it's based on a crosstab or pivot table. And in this case, what we're going to look at is we're going to look at question 14, 24, and 34 from our data frame 3, which is our customer relationship management data set. So let's just take a look at question 14, 24, and 34. Hold on, take a moment to load up here. All right, so question 14 asks about their preferred follow-up method, and we asked that question in March and April and May. So you see we have 3 groups here. We have the March group, the April group, the May group, and in this case we have nominal data because they choose how they would prefer to be contacted by email, in person, text, phone, and so on. So what we're going to do is we're going to code the data. It is not already coded in this particular data set. So we need to replace email with a 1, in-person with a 2, text with, well, in this case, we're going to just look at email and not email. Okay, let's simplify it here. So we'll do email and not email, which means in-person, text, and phone we'll label as 2, email as 1, and we'll remove the no follow-up. Since they don't want to be contacted, the contacting method is not relevant. So we'll make those the NAs. So what we're going to do is we're going to create a copy of the original data frame, and that way we can do this replacement, and we'll do it in place. So we'll just change out that variable values in the table. And so we'll import numpy as NP in order to allow for this replace. And we can see, I'll just load up CQ here. And so we can see question 14, 24, 34. You can see 34 on this here. Actually, you can't because my head's covering it up. But you can see it's now replaced by numbers. If you want to just see directly, let's do CQ question 14. We can see we all have numbers now, and our numbers are 1 and 2. So email and not email. So then we can create a crosstab from that, from Pandas import crosstab. We've done that before. And then our crosstab, again, we're deciding what is going to be on the rows and what is going to be the columns. And the key here is that this crosstab or pivot table, we actually have 3 variables, not just 2. So you'll have a single index. Here we start with question 14 with the email, no email. And then you'll see here that we have question 24, email, no email. And then we have question 34, email or no email. So what we have here when you see it displayed in the crosstab is that within question 24, are they email or no email within question 34? So it's tying these two together and saying if they said 1 and 1, that's the column. If they said 1 and 2, that's this column, 2 and 1. So it's trying to see a 3-dimensional table 2-dimensionally. So we create our crosstab. Okay. And then to do our test, what we do is from statsmodels.stats.contingency_tables, that's where you find Cochrane's Q. So from statsmodels.stats.contingency_tables, import Cochrane's Q. And Cochrane's Q is one of those that in order to get it to provide the output, you have to tell it to print. So print Cochrane's Q, and then it's going to do that test based on the crosstab, the pivot table. So that's why whatever you called it here, we called it mn_cross. Then we would have that same label here. So when we do that, what we find here is that we have a p-value of 0.39. That p-value of 0.39 is greater than 0.05. Remember, if the p-value is less than 0.05, then there is a difference. In this case, what we're detecting is we're detecting no difference. Now, no difference could be because of sample size, or it could be that there truly is no difference. And that makes kind of sense, right? If your preferred method of being contacted is email, it's probably always email. I think there was email or no email, right? Yeah. Email or no email. If your preferred contact method is email, it's probably always email. It's not going to change from March to April to May. And so we don't actually expect this one to be statistically significantly different because that's really not something that changes about people. Okay. Now, I just want to point out to you what would happen if I tried to do multiple categories besides just the binary email, no email. So let's go back and let's suppose that I make it email, in person, or we'll call the rest of these other essentially. So let's just run this again. And so now you'll see that we have 1, 2, or 3 as options here. And again, if we then create our crosstab, you'll notice our crosstab now has 1, 2, 3, 1, 2, 3, 1, 2, 3. But notice now when I run this, I can do the Cochrane's Q with more than just the binary. I can run it with the 3 scenarios. Again, it is not significant. So you can see there that there's no difference. People aren't changing. Even if we flesh out more than just email, non-email, email, in person, or other, it's still not changing. Now you could drill down, you could look closer, because of course we want to, if this was significant, we could say, okay, well, where is the relationship, where is not? And you would have to break it down in terms of each of the crosstabs. So you would have to essentially say, okay, let's compare question 14 and 34 and look at just this one. Do we see a difference? And then look at 14 and 24. Do we see a difference? And 24 and 34. So you're looking at here. And in these cases, when we look at this, we look at 14 and 34. There's clearly that in May, there's one kind of pattern. So take that back. This is March and April. So March and May. In March and May, if we're looking at differences, it's not particularly clear from the crosstab that there's a difference here. So in fact, what we see, if we look at the crosstab, see how the biggest number is 1 and 1, 2 and 2, 3 and 3. That's because the people who like email still like email, and the people who like in person still like in person, and the people who like some other methods still like the other method. So the biggest numbers are here on the horizontal. That's because there's no difference, no statistically significant difference, and how people like to be contacted between here. This is between March and May. If we run the same thing here with March and April, again, biggest numbers on the horizontal here. And if you run it again here, this is with April, May, again, the biggest numbers on the horizontal. So people don't change as we go from March to April to May. And it didn't really matter whether we classified it with binary, with email, not email, or whether we expanded it to more categories of email, in person, and other. You can do all those in Cochrane's Q, but again, it's nominal data that we're comparing same people. So typically it's across time. All right, so what if our data is not nominal? What if instead, as we look at here, what if we have ordinal data? So there's some ranking to the question that we're looking at. So let's go to that example here somewhere. So we're using Friedman's test, and let's compare question 11, question 21, and question 31 from data frame 3. So this is from the Customer Relationships Management database. So let's go look at question 11, 21, and 31. Question 11 is interactivity in March. So each salesperson after the call actually is going to rate how they felt that interaction was on a scale of 0 to 10. So because it is a rating, 0 to 10, then it is ordinal. So we're going to look at our ordinal data here using Friedman's test. So Friedman's test, we're going to get from skippy.stats. We're going to import what's called a Friedman chi-square. So same chi-square that we've been seeing before. Chi-squared is a distribution, like the normal distribution, and can be used for a number of tests. So let's import from skippy.stats Friedman's chi-square. And then what we're going to need to do is we're going to need to take our data frame 3, and we're going to condense it down into just the 3 variables we're looking at, because the Friedman's test doesn't do well if there are empty values. So we need to make sure that we're only dealing with, so there's no missingness. And the important thing here is that the missingness, if there's missing for any of one of the 3, then we can't have that entire row of information. Because if we're doing paired, or in this case, we have a third, so it's more than a pair. But if it is the same people in all 3, we need to make sure that we have information for that same person in all 3, because we're matching them together. So we need to make sure that we drop any empty rows in any cell is empty. If we're looking at question 11, question 21, question 31, we will remove the entire row of information if even just question 11 is missing, but 21 and 31 are there. So this next line of code creates this new table from the data frame 3 that it consists of only Q11, Q21, and Q31. And let's just run that. So then you can see here what this looks like. We just have our 3 columns of information, 11, 21, 31, and we've gotten rid of any rows that are missing any data. Then we do Friedman's chi-squared. We're going to pull from our new table here, question 11, then question 21, and question 31. So we can run that. We get a p-value of 0.0169. That is less than our alpha of 0.05. So there is a difference in the rating. Remember, this question was about call interactivity. So the interactivity rating from 0 to 10 is changing. So same person each time, but that rating is changing over time. So it's not like the interactivity with person X is a 6 and a 6 and a 6. We're detecting that there's a change, that it might change and it might be going up or going down. So we can dive deeper into this, and one way to look at this is to look at it with data visualization. So in order to see this on a graph, the fact that it's different, then what we're going to do is we are going to create here, we're going to create 3 data frames that are going to have our interactivity, and we're going to have our interactivity for each of the months. So we're going to separate them out, and then we're going to add them because they need to be in a little bit of different format in order for us to build our graphs. So step 1. Step 1 is we are going to essentially create a list that is just the number 1 repeating over and over and over again for the length of question 11. So if we look at, let's just go here, code, the length of DF3, question 11. So this is how many, not length, there we go. So there are 63 entries in question 11. Remember, question 11 is the interactivity in March. So there's 11 reported ratings for interactivity. So each salesperson and the person they interacted with gave a rating. Okay, we want to do this. We want to repeat the number 1 as many times as the length of that variable, question 11. So we're going to use NumPy. That's the NP you see here. We're going to repeat. We're going to repeat the value 1, and we're going to repeat it for the length of question 11. Then what we're going to do is we're going to repeat the number 2 for the length of question 21. Then what we're going to do is we're going to repeat the number 3 for the length of question 31. So this is going to give us 3 lists that are just 1, 1, 1, 1, 1, 63 times, and 2, 2, 2, 2, 2, probably about 63 times. Okay, then what we're going to do is we are going to create a data frame, a table, that is going to have the month, and our month here is going to be this DF3 length of question 11. So this is going to be that 11111 month label. And then we're going to have a column called interactivity, and we're going to pull the values from question 11. So we're creating basically a table that has 2 columns. One is the month, which for the first data frame is going to be 111111. And the second column is the interactivity, which is taking the responses from question 11. And we're essentially going to do that for group 2, which is question 21. So it's going to say 2, 2, 2, 2, 2, and it's going to have the values from the interactivity in April. So that's question 21. Then we're going to create another table that is month 33333. So it's just pulling from this. And then it's going to be the values from question 31. So it's going to be those interactivity ratings from May. So I'm going to run this, and then I'll just show you what it looks like. So here is VP3.head. So you can see a column of month and a column of interactivity. Okay, why do we go through all this? Well, because the graphing method we're going to use requires that we have a table with 2 columns here, and we need to take this first data frame where the month is all 111, and we're going to stack it so that that table is on top, and then we're going to take the next table, that's the 222 month, and then stack it there, and then we're going to take that third table, it's also 2 columns, month and interactivity, and we're going to put it below. So to do that, to take these 3 tables and put them on top of each other, we are going to create this new table called VP123. You can call it whatever you want. And it's going to use pandas, so we have to make sure we have imported pandas as PD. And then we're using the command concat. So we're going to concatenate, and you put it in the order. So we're going to take table VP, and then table VP2, and then table VP3. So when we do that, then what we've done is created a table that has month and has interactivity, and you see that the first table is here, and then we've just added below the next tables. So in order to do that, in order to concatenate these things, we need to have created tables that matched in terms of the column names. So that's why we did this step where we did month is the name of the column using our dictionary method here, variable, value, variable, value. And so we did month, and then we used that repeated, and then we did our variable interactivity and pulled from the information. So we're formatting it so that when we go and use the package violin plot, or sorry, the package Seaborn and the command violin plot, it will then plot the information. So we're actually creating a graph that looks like this. This is a violin plot. And so what it's showing you is it has the box plot within it. So here's the middle 50%. Here is Q1, that's the 25%. Here's Q3, the 75%. Here is our range of values. And then it adds to that and shows you how many. So not only our range here, our interquartile range, but we can also see kind of more the distribution. And we can see that there's more responses here and, of course, less responses here. So you're getting that kind of histogram type distribution attached to it in the violin plot. So what I'm looking for is there a difference as we look across in terms of the median, in terms of the most likely responses? Are they shifted? So to create a violin plot, we do from Seaborn, import violin plot, and then we use the command violin plot, data equals, it needs to be a table, and then you specify the x-axis is the variable month, and the y-axis is the variable interactivity. So it needs to match the names of the variables inside of this table, which you can see we created was month and interactivity. Then we're going to call the x-axis month, the x-axis labels. We can see that the code here, we want to call it April, May, June. If I remove this and go to run it, all right, I get an error. All right, so we got to figure out what this error problem is. It says cannot re-index on an axis with duplicate labels. So this is a problem with the new version of Seaborn. The previous version, you would have the code like this. It would run fine. They've updated it. And so it tells you the issue is an index issue. The solution here is to put .reset index. And the issue is because when we concatenate these 3 tables together, they each had their own index. And so when it puts the 3 together, we want it so the index is reset for the whole group. If you're doing it separately outside, it doesn't seem to fix the problem. So we'll put it in here as reset index and run that. When we do that, you see the labels are now 1, 2, 3, because that's what we had told it when we were doing creating it. We had created 1, 2, 3. And let's just go back and see, what if we had made this March, April, May. So instead of putting the numbers 1, 2, 3, let's just give it a quick try. What happens if we create a table where instead of saying 1, 2, 3, it says April, May, June. We put that together. Let's try running it. Let's see how that goes. Okay, so there you see we have it as March, April, May already written in. If your data was coded separately, so you had the 1, 2, 3 label, you can replace that with the command line that you see here, which is take these tick marks, and in fact it's position based, so it's going to be starting your count 0, 1, 2. You would say here's position 0, here's position 1, here's position 2, label it March, April, May. So this line of code here would then relabel them. If we had used 1, 2, 3 here, looks like we can go and we can make it say March, April, May, and then we have those labels here as well. So you have the options available to you. You can either edit the labels here with this plt.xticks, or in this case, if we already changed the labels up top at March, April, May, then we can simply just run it and it will put them in here. Okay, so we have looked at, if we go back to our table here, we've looked at 3 or more groups, same people in all the groups. We looked at Cochrane's Q if it was nominal. We looked at Friedman's test if it was ordinal. If it is ratio and intervals, so counts or measures, and we can assume a normal distribution, then we're using what is called the repeated measures ANOVA. So let's take a look at how the repeated measures ANOVA works. To do repeated measures ANOVA, we're going to need statsmodel.stats.ANOVA, and it is ANOVA RM. So we are doing repeated measures ANOVA. So recall the ANOVA from the previous video looked at comparing groups, and this here allows us to compare when it's the same people. So it's a repeated measure. So we often have before, after something else. All right, in order to do repeated measures ANOVA, you need to take your variables and put them together into a table. So we're going to take data frame 3, which is the customer relationship management database. We are going to subset it to just question 10, 20, and 30. And so 10, 20, and 30. 10 was the longest customer monologue by seconds. And so it's the longest stretch of time that a customer speaks uninterrupted. So we're going to take that information in March and April and May and see if there is a change. How are our employees doing at not interrupting our customers? So we're going to create a table from the original data set, but this one's going to consist of just question 10, 20, and 30. And then we want to drop any row that doesn't have information for question 10 and 20 and 30. So they need to all be present. All right, so let's import our packages. Let's create our subset. We can look at it, df3b. Oh, should have just done the head of it instead of the whole thing. My internet crapped out. Come on. You do now. All right, having some connections. There we go. All right, finally showed up. DF3B, we can see this is the whole thing, not just the head. The head here is the top 4. So you can see question 10, question 20, question 30. So it had some connection issues. That's why it was running slow and why it says saving failed. All right, so now that we're reconnected, then what we're going to do from here is we're going to take this information, and in order to do our repeated measure ANOVA, we have to reformat this so that we have one column that is the monologues. So we're going to create one column that contains question 10 and question 20 and question 30 all in a single column. And then we'll create a column that has our labels for our March, April, May. So just like we just did with our, we are creating our violin plots, we're going to do the same thing here. All right, so let's go in. So same process, right? So we're going to repeat using NumPy. We're going to repeat the number 1, and we're going to repeat it as many times as our responses for question 10. So for the length of question 10. Okay, and then we're going to repeat the same process. So we're going to repeat the number 2 for the length of question 20. And we're going to repeat the number 3 for the length of question 30. So we're creating these lists of just 1s, lists of just 2s, lists of just 3s. Okay, so same thing as we did before with when we were setting up our violin plot, right? All right, so then what we're going to do here with our repeated measure ANOVA is that we are going to create a data frame. And so we're going to use the dictionary approach. So here we have our variable month, and here we have that 11111. And here we have monologue, and we're going to pull the values from question 10. And then what we're going to do is tell it to reset the index for that as we concatenate them together. So you can see here we're trying to deal with that index issue that we saw with our violin plot here with our, to do our ANOVA. So we're going to repeat this. We're going to create a second data frame, which is month and monologue, and reset the index here. Then we are going to take month and monologue for 3. The difference with what we're doing here versus what we did with the violin plot is we're actually going to create a variable that's called index from the index. So when we merge these together, we'll end up with actually 3 columns of data, the month, the monologue, and the index. And that way we're going to be able to use it in the ANOVA test. Okay. So we're going to concatenate those 2 tables. So we're going to stack them on top of each other. And what we see here, I'll just show you what this looks like. 1, 2, 3. Is that we have our monologue, we have our month, and we have our index here. And so for each month, we have the full index, the 0 through 134. And then for month 2, 0 through 134. So we reset the list, but we reset the list for each table, not for the combined table like we did with the violin plot, where we did it at the very end. Because we're doing it each one, we have our index going from 0 to 134 for month 1, and then 0 to 134 for month 2, and 0 to 134 for month 3. The benefit of doing that and not using so we had in place equals true, but we weren't telling it to drop the other index. We were saying keep both, is that it created this variable here, index, this column, which means when we go to do the ANOVA, the way we do an ANOVA is we're going to say, let's compare monologues. And the subject, the person, is going to be represented by the index numbers. So person 0 in month 1 is also person 0 in month 2 and person 0 in month 3. And then we're going to do within the month. So we're looking for the effect of month. We're looking for the effect of person. We're looking for differences in monologues based on the combination of person and month. That's how an analysis of variance works. And with repeated measure, it's because we have the same people in each month. So if we do that, when you do ANOVAs, ANOVA RMs, we're going to have to do print and .fit. So it does require a little bit different formatting for calling this test. Let's just make sure I've run all this. Kind of lost track of what I clicked on and what I didn't. All right, import packages, create a subset, drop the NAs. We just looked at an example of what it looked like. We then created these lists of all 1s, all 2s, all 3s. We then created 3 data frames that had the month and monologue because they have to be formatted the same to put them together. And we added the index as this new additional variable. We put them all together. We created one table that has index, month, and monologue. And then we print the results of our ANOVA RM, where the data table is ARM 123. Our dependent variable is monologue, our subject is index, and within, make sure you put the brackets around it, is month, and then .fit. When we run that, we get our test. Here, our p-value is greater than our alpha of 0.05, and so what it's telling us here is that when we look at the month, there is not a significantly different monologue length of time the person talks between the different months. Okay, we're not seeing a difference in March, April, May of the different lengths of monologues. Okay, we could look at this with that violin plot. Let's see if we can get this violin plot to work. From Seaborn, import violin plot. Violin plot is going to use that ARM 123 table. X equals month, Y equals monologue. PLT.X label is month. And here, because we have that because we have the labels 1, 2, 3, if we remove this, it'll just say 1, 2, 3. See if this works. There we go. So you see it just says 1, 2, 3, and so we can then change that out to be April, May, June. Okay, so we can plot here and we can see why the test did not find a statistically significant difference. Because the monologue lengths, look, they have very much the same in terms of median, in terms of mean, right? These distributions don't look a whole lot different in the 3 different time periods, so it makes sense that it wouldn't find anything statistically significantly different. So our p-value is greater than 0.05. We can't detect a difference. Either there is no difference or there's a sample size issue.